in this video, you are going to learn the kinetic molecular theory. As we have seen before, for a gas molecule or many gas molecules, they are in random motion and they will have a chance to hit on another molecule. Some of them will have to travel longer than the other. Some of them, for example, this one is going to travel in a very short time before hitting this one over here. That's why we have a mean free path. That means the average free path. That means some of the molecules will travel faster and or travel further in order to hit the other molecule. Okay, since they are not traveling at the same velocity, then we can just make a plot. Let's say if I want to plot velocity, in other words, velocity is similar to speed in our case, versus the number of molecules in that velocity, number of molecules, you would typically see a graph look like this. That means the majority of the molecule travel at the velocity is over here. See, if you plot, you go and see the number of molecules traveling at this velocity will be the highest number. And we call that the peak number, okay? Because there are many molecules moving at this velocity. However, this is not the only velocity. It can move at this velocity, it can move at this velocity, and there are certain number of molecules actually moving at very high velocity, but not too many of them. Okay, if this curve is symmetrical, that means the peak value should be equal to the average. However, since the curve doesn't always look symmetrical, that's why when we make the plot, here's velocity, and here's the number of molecules. So what we can see, for example, if the peak go like this and the tail go like this, so over here, this is the peak. However, the average will be on the right side of the peak if we take the average. And that's what we call this root mean square. RMS means root mean square value of the velocity. Let's talk about the kinetic molecular theory. Kinetic molecular theory. What it says, it is the thermal energy of any gas molecules will be equal to thermal energy will be equal to 3/2 of RT, where T is the temperature in Kelvin, and R, this R, we have to pay attention here, because when we use the ideal gas law, we said the R will have the unit of ATM, that's the unit for pressure, atmosphere, liter, that is the volume we typically use in chemistry, divided by how many moles, and Kelvin. Okay, this is not the standard unit, not the SI unit. Now, because we are going to calculate energy, and very likely we are going to convert it to kinetic energy, so we are going to use the SI unit over here. That means we need to use joules. And by the way, if you use this unit, the R will be 0.08206 with this unit. If we use a more SI or the SI unit, we are going to see 8.314, and the unit will be joules per mole K. So this is the SI unit for the R. And this one is the popular unit that we use for the R for the calculation for the ideal gas. PV equal to nRT. Okay, so how do we use this kinetic molecular theory? Let me repeat again. It says thermal energy of a gas that is equal to 3/2 times RT. Thermal energy, it can be converted to another energy, and in our case, since the molecules are free to move before it hits the other molecules, so we can actually calculate its kinetic energy. So kinetic energy is equal to half mv squared, where v is the velocity. From now on, we are going to use a letter u instead of v. Why? Because earlier the chapter we used v for volume, so let's not make any confusion. From now on, let's use the letter u. So over here, u, that is same as velocity. So kinetic energy, it is the same as the thermal energy now. Thermal energy, it is 3/2 times RT. Here is the mass. As for a gas molecule, the mass it is same as its molecular mass or molecular weight. Let's say I would like to know the velocity over here. And by the way, this velocity is the average velocity, and we can call that the root mean square velocity. That is the average. So what is my root mean square velocity if I try to solve it? The two over here can be canceled out. So what happens is if I move the m around to this side, what I will get is average velocity or root mean square velocity that is equal to 3 times RT and divided by m. Okay, let me put it this way. M is the molecular mass, or we can say molecular weight. It typically will have the unit of, from what we have seen before, it is gram per mole. Since we are going to use everything in the SI unit, and therefore we prefer to have kilogram per mole. Okay. If you look at this formula over here, what we can see is what happens if the molecular weight of the gas is higher. What will be the velocity over here? Let's see. If this number is higher, that means this number will be lower because here is the denominator. With the same reason, if I have a graph like this is a plot of velocity versus the number of molecules. Let's say I have two different curves. One curve will go like this. The other curve, let's say it go like this. The question will be, which one will have a higher molecular weight? Okay, so let me repeat what the question is again. Here is a plot of two different gases. It's a plot of molecular distribution or number of molecular molecules versus velocity. I would like to know which gas will have a higher molecular weight. Let's look at it. For this one, the average velocity is over here. For the red curve, the average velocity, let's say, is over here. From this curve, we can see that the blue color curve will have a higher velocity. If it has a higher velocity, that means it has a lower molecular mass. If you look at this formula over here, velocity, if this number is higher, that means this number is lower. Likewise, over here, it has a lower velocity. That means this one over here with the red curve, it will have a higher molecular mass. Higher molecular mass or molecular weight. All right. Let's work on an example and try to use this formula to calculate the velocity of an actual gas. We know that in air, the majority of the gas, it is nitrogen. It is about 80% occupied in air, that is nitrogen. And the molecular weight of nitrogen, that is equal to 2 times the atomic weight, is about 14 grams per mole. So everything together, it will be roughly about 28 grams per mole. If I have to convert the unit to SI unit, I have to make it equal to 0.028 kilogram per mole. Okay, so what we want to calculate is what is the velocity of nitrogen molecules in air at about room temperature, that is 25 degrees Celsius. Okay, 25 degrees Celsius, it is not an SI unit. SI unit is Kelvin, so we are going to convert that into Kelvin. That plus, so that is equal to 298 Kelvin. All right, so from what we have shown before, it is average velocity or root mean square velocity, that is equal to square root of 3 times R T and then divided by the molecular weight. Let's plug in all the parameters. That is equal to square root of 3 times R. R in this case, if we carry the right unit, it will be 8.314 joules per mole. Okay. And temperature, that is 298 K. So the K can be canceled out. All right, and then divided by the SI unit of the molecular weight will be 0.028 kg per mole. If we put everything in the right unit, in the SI unit, what we expect is to have the unit of meters per second. Okay, so we punched everything into the calculator, and what I got was 515 meters per second. That is very fast, and let's compare that to the speed of sound. Speed of sound at room temperature is about 430 meters per second. So that makes sense because the sound uses the air to transfer the energy, and the speed of sound cannot be faster than the motion of the molecules. So that makes sense.